Hello, this is a video on bringing up the TangerineSDR software-defined radio. This is a set of boards that are being produced by Tapper. The current project is using a Max 10 development kit due to lack of availability of FPGAs on the open market at this time. In addition to that, there are a couple of other modules that are needed. Ultimately, the development kit will be replaced with the actual data engine module, but this video applies to the system using the Max 10 development kit. This presentation is in three parts. This first part is essentially a PowerPoint type presentation with slides and discussion. The second part will be a video walkthrough of bringing up the FPGA code image and the software stack and getting it to run. And the third part will be using a Python command line interface for using the localhost data engine protocol and talking to the unit. The prerequisites for bringing up the system are that you have a Max 10 development kit, which is labeled DEV-10M50-A, and this is a unit that has an HMAC connector and 2 gigabit Ethernet connectors on it. It includes a wall wart power supply and a USB JTAG programming cable. We'll be connecting the cable to a Linux computer, and that JTAG interface allows downloading the FPGA image and downloading the software image to the module and interacting with it. The computer needs to be running Linux. It's recommended that you use CentOS 7. In this demo, we'll be running it on Ubuntu 20.04, although there are some difficulties getting Ubuntu to work with the Intel Quartus software. It takes some configuration effort. The processor needed should be fairly powerful with between 8 and 16 gig of RAM, at least one USB port and an Ethernet connection on the same LAN subnet that the development kit is connected to. The software runs the Altera Quartus 20.1 image, which you can download from the Intel website, and the NIOS Eclipse software, which comes bundled in the Quartus package. Also, I suggest using Visual Studio Code to run the Python-based CLI, but that's not strictly necessary. It can be run under a terminal window as well. Ubuntu 20.04 has been used, but does have some issues. And the USB port in the dev kit are connected via the supplied cable. You also need a gigabit Ethernet switch, which provides DHCP addresses to the clients. The current software load does not allow a static IP address on the development kit. It will automatically get an IP address from the DHCP server. You'll need the TangerineSDR data engine adapter board. This is not the data engine, but the adapter that goes between the development kit and the other modules. You'll need a TangerineSDR clock module, revision A. There are 2 reworks that need to be done on the clock module prior to doing this particular test. You'll need a GPS antenna that will be connected to the clock module via an SMA connector, and you'll need a TangerineSDR receiver module. The TangerineSDR software is located currently on my GitHub, github.com/Tom-McDermott, and the project is called TSDR-dev. This is the test phase 1A package, which has passed the test phase 1A. It doesn't do a lot right now. The receiver doesn't provide any samples, but what it does do is bring up a TCP IP stack, brings up UDP sockets, and it talks to all of the peripherals in the test system so that you can, using the command line interface, interact with the peripherals on the board. It will discover TangerineSDR using the OpenHPSDR protocol. It will automatically open up a provisioning channel and provide commands to read and write the module control registers using the LHDE protocol via UDP sockets, and that will print ACK, NAC, and text response to the command. Videos on this project will be at youtube.com/@N5EG. The preliminary steps for the dev kit only, prior to connecting the dev kit to anything else, we'll recommend that you bring up the factory pre-installed image. And it's possible that that factory image may get overwritten, but that's the intention of the dev kit. It comes with a pre-installed image that will become overwritten as you deploy your development image. You'll power up the dev kit with its included wall-wart power supply and use the web browser to verify connectivity to the default dev kit preloaded software image. All of these are steps that are documented with the manual that came with the dev kit itself. I recommend that you write down and safely store the MAC address and the serial number of your dev kit board. The serial number should also be on a white paper label that's glued to the dev kit board, and it's possible to reconstruct the Ethernet MAC addresses from that serial number. So this is an overview of the steps. We'll go through these steps in detail when we bring up the system in section 2. So you need to first install the free version of Quartus 20.1. Usually that's called the light version on the Intel website, and it needs to be installed onto CentOS 7. You need to ensure that the clock module version A has the 2 reworks done to it. You need to install the clock and receiver modules on the data engine adapter, and you'll need to install the data engine adapter onto the dev kit HMAC connector using the supplied standoffs. All of this, of course, is done without power being applied. The power is applied through a right angle power connector, which is somewhat of a tight fit, and so you'll need to install the data engine adapter onto the dev kit and then provide a little bit of wiggle room to get the power supply connected. You'll then need to configure the dip switches that are on the dev kit. There's a photograph and a couple of slides on how to do that. Install Git on CentOS 7 if it's not already there. Install Python 3 on CentOS if it's not already there. And then you will git clone TSDR-dev and TSDR-util from the GitHub site link provided in the previous slide onto their respective directories on CentOS 7. You'll connect the USB JTAG and Ethernet connections to the development kit. You may need to set UDEV rules in Linux for it to recognize the USB JTAG device. This is Linux version dependent, and you may or may not need to do it. If your version of Quartus does not find the JTAG device, that is an indication you may need to set UDEV rules on your version of Linux. And after that, you'll power up the development kit. There are 2 types of usage for the system. If you just want to run existing code and you don't want to edit or recompile, then you can use the already built SOF file to the dev kit and start the FPGA. You'll download the already built C code image to the FPGA and run it, and you'll start the CLI on the Linux host and run it. And that's the purpose of this video. You can also modify the Verilog and/or C code, but more extensive work is needed, including editing the board support package due to some hard-coded file paths in that package, resynthesize the Verilog platform designer, sometimes called QSys package, recompile the Verilog. You'll need to rebuild the board support package, which configures the C driver. You'll need to patch the Ethernet driver code and recompile the C code. That's not the subject of this video. Note that the instructions provided in Quartus 20.1 for doing this are not correct. There's a file called weird_stuff.txt in the root of the TSDR dev directory, which will provide detailed directions for rebuilding the board support package. In terms of cabling, this is a photograph. The dev kit is the green board on the right. The orange board is the TangerineSDR data engine adapter. You can see on top the clock module is installed into the M.2 connector, and you cannot see underneath the receiver module has been installed and connected to the data engine adapter on the bottom. The micro USB to USB-A cable is the JTAG interface. You can see this is plugged into the upper of the two micro USB connectors. The Ethernet cable is plugged into the bottom Ethernet receptacle on the board. It's a little difficult to see in this picture, but there are 2 gigabit Ethernet connectors on top of each other. You'll want to go to the bottom one. And then on the left, you'll need to connect up a GPS antenna. And in this case, this system is using a BNC to SMA adapter to connect it to the center interface. And you can see the blue wires on the clock module showing that this has been reworked. The power from the dev kit wall wart is connected to the barrel jack, which is right next to the data engine adapter via a right angle connection. And you can see it's just a little bit of a tight fit, but you can get it in with a little bit of wiggling. There are 2 dip switch packages on the development kit on the rear side, so you can get to these switches even if the data engine adapter has been assembled to the HMAC connector. Switch 2, the upper, needs to have switches 1 and 2 in the off position and switches 3 and 4 in the on position. And switch 1 probably doesn't matter, but in this case, switches 1, 2, 3, and 4 are set in the off position. The dip switch package has a label marked on so that you can tell which position is on and which position is off. Past this point, we'll now go into a detailed walkthrough of bringing up the Quartus system, bringing up the image, bringing up the software image, getting it started, and showing that it's successfully connected to the local area network with DHCP. The last part will be a walkthrough using the Python command line. We will now start the software on the system. It's been installed into the directory TSDR-dev under the home directory. So we'll launch the Quartus environment, and we'll want to open up the file. And in this case, we'll go to the home directory, TSDR-dev. The sample project is DevKit Simple Socket Server. And then the type of file will be a project file, QPF. And we'll open top.qpf. These may show up on the recent projects list, which can save you a step from having to bring up the window and select the project. It takes a little while for Quartus to start up. The next thing we'll do is go to the Tools menu, and under Tools, we'll go down to Neos 2 Software Build Tools for Eclipse and start that. And for the project, what we will select is the DevKit Simple Socket Server Project / software folder under that, or we can browse for it, and it'll be Simple Socket Server Project and then the software folder, and then click OK. This will then bring up the software development environment. The next step is to go back to Quartus by selecting the Quartus icon. We will now program the FPGA code into the box. We go up to the programmer icon in the top center of the window and select that. And if no hardware is set up, you can select the hardware setup button in the upper left corner and then find the hardware called USB Blaster 2. This is provided by the development board, so the development board obviously is powered on. We'll close that, and now we'll click the Start button, and the Start button will now download the soft file to the FPGA. This is an unlicensed version of the Lite software package, and some of the modules in it are time locked. So it will run for 1 hour, after which time it will time out. The 1 hour is just per instance, it's not cumulative. So you can let it run, and if it times out, you can close it and start back up again and still get 1 hour of time. Now that we have the image downloaded, we need to start the software. So we'll go to the Eclipse icon and bring this up. We will now click Run Configurations. We'll bring up the Run Configurations window and select Target Connection. Sometimes Quartus takes a few minutes to find the same JTAG interface that the hardware program has used. And so we can click the Refresh Connections button. We may have to do this a few times over a couple of minutes until it finds it. We'll again click Refresh Connections and let this come up. What this window does is to tell the Neos software what target it's going to use to download software. The Neos software uses the same JTAG interface that we use to program the FPGA hard image to download the software. This system downloads the software into the DDR3 RAM on the board. Now you can see it's populated. It says USB Blaster 2 on localhost 1, so we can close the window. We'll go up to Run and click the Run dialog box. We'll now see it downloading the software to the target, and it now brings up a console window. It takes a few minutes for it to boot up. You can see that it's auto-starting, auto-initializing. It's found the board. It's started up at address 0000. It's then gone out via DHCP to the Ethernet interface and found a DHCP address, in this case 192.168.2.8 with a subnet mask and a gateway. It's then started up the UDP socket server. It's initialized the GPS module, and the response message 6205 twice indicates that it accepted the GPS initialization commands and has programmed the GPS module into the correct mode, putting out the right reference frequency on the clock and putting out pulse per second. You'll see the pulse per second LED on the clock module start flashing once per second. It's then identified and found the Silicon Labs 5345 synthesizer and read the device type number from that device using the I2C interface as 5345. This is the correct type. It started up the socket server task, and it's correctly initialized the synthesizer without errors. At this point, the module is responding to socket requests using OpenHPSDR protocol. The GPS module is up, providing the correct frequency. There is a 10 megahertz output available on a small connector on the data engine adapter board, and it's providing 122.88 megahertz to the receiver module and the FPGA on the board. In part 3, we'll go look at using the Python command line interface to bring up a protocol handler so we can investigate some properties. In this part, we will look at using the command line interface to talk to the module using the localhost data engine protocol. So the first thing we'll do is open a folder, and the folder we want is called TSDR-util, and we'll open up the TSDR-CLI folder. And then we will bring up the DE CLI and DE connection.py. Connection manages the socket connections to the module, and CLI provides a text interface. Bringing up the DE_CLI module, we'll click Run without debugging, since we're not going to be debugging Python, and that will bring up the interface. And here what it does is it first uses OpenHPSDR Discovery to go out and look for an OpenHPSDR module that answers the discovery. In this case, it's found the module on 192.168.2.8, and successfully identified the particular unit. We now have available to us a few commands that implement this module. The first thing we'll do is send the P command, which opens and allows us to send a provisioning command. The protocol lets us read and write registers on the target, and it identifies them by a module number, and on that module, an interface number. We have two modules in the system. Module 0 is the clock module, and module 1 is the receiver module. And each module has multiple interfaces. So what we'll do in this case is we'll do a module read MR command, and it's to module 0, OX0000. We're going to read the ident ROM on the module, which is OX0002, and then we have a couple of null fields, OX00, and this will read a unique 72-bit serial number that's been programmed onto the clock module. In TangerineSDR, every module has a unique serial number. So we'll issue the command, and we got an ACK response, an AK. We'll now issue the R for read, and we can read the response that it sent. And up in the middle of the terminal window, it says read response from module 0, interface number 2, and it reads the unique 72-bit serial number from the module. We'll now read the command from the receiver module, so we'll enter a provisioning command, module read. The receive module is module 1, OX0001, and this has only two interfaces on it. The interface with the ident serial number is OX0001 with a couple of null bytes. And now we got an ACK, we can read the response. And here now we see the unique 72-bit serial number from the receiver. We can also issue a provisioning command, module read, the receiver module, OX0001, and the interface number 2 is the SPI interface. And we want to read on that SPI interface the address number 2 on that particular interface. And if we read the response on that, we get an OX55, which correctly identifies the analog devices chip is responding to the SPI command. There are a few other commands here, but at this time, we'll leave it at this. You can explore the module identifier and interface identifiers are in an interface map table in the C code. And when we come to other systems that don't use the data engine adapter and that use the actual data engine and may have more receive modules, this table will change so that the interface and module numbers will probably change, but they'll be defined in that particular table. We can now quit the interface and go back. So that's a brief walkthrough of bringing up the interface on the particular module. In order to shut down the system, we go to the NEOS console. There's a red button just above the NEOS 2 console. We click red, that will stop the software that's currently executing on the target. We can then close and exit Eclipse. The next step is to bring up the status window for the open cores and close that. That will stop the 1 hour timer, which again is not cumulative. We then need to bring up the programming window from Eclipse and close the programming window, and then we can close Eclipse itself, and that will gracefully shut down all of the processes. While this portion of the project is just the very beginning of the software and the FPGA code on the road towards a working software-defined radio, I'd like to acknowledge the help of a lot of people to get this far. Scotty Cowling has done a huge amount of work. He's the project lead for the TangerineSDR project, the system designer, the architect of the system, and he laid out and fabricated all of the hardware modules. John Ackerman, N8UR, designed the clock module and has provided help in the commands to initialize the clock module. Dave Witten, KD0EAG, has worked on the magnetometer and magnetometer software. Dave Larson, KV0S, has worked on the TangerineSDR.com website. Nathaniel Frizzell, W2NAF, is part of the HAMSci project and a professor at the University of Scranton and is the principal investigator on this project. And we'd like to gratefully acknowledge support for this project from the National Science Foundation through a number of their grants. All of these have been instrumental in getting the project to this phase.